Welcome back to 6.1 Notes, where we're taking a look at the periodic table. In the last podcast, we talked about the historical development of the periodic table, and we're now currently looking at some of the properties, the repeating properties that the periodic table shows. All right, and specifically, we're going to be taking a look at metals, nonmetals, and metalloids. As it turns out, the periodic table has a repeating pattern on where the metals, nonmetals, and metalloids are located. For example, and I'm going to change my color here to red. As you go down and to the left on the periodic table, down this way, elements tend to be more metallic. All right. Conversely, if you go up and to the right on the periodic table, they tend to be less metallic, or what we call non-metallic. All right. But there is a little area in the middle where the properties start to overlap. It is a continuum. We would say francium and cesium are the most metallic elements, and we'll talk about what properties make them metallic. We would say that fluorine, would be the most non-metallic element if you ignore what are called the noble gases over here. And then there's a continuum. We would say that iron, even though it is clearly a metal, it is less metallic than, say, cesium. Or on the other hand, if you go over to this side, sulfur, though it is clearly a nonmetal, is more metallic than fluorine. Fluorine is the most nonmetallic element. In the middle, you have a set of elements that share properties of both metals and nonmetals, and those are called semimetals. And I'm going to draw a staircase in green here as you go down the periodic table, and that's kind of where this overlap happens, where you have boron, silicon, germanium, arsenic, antimony, tellurium, polonium, and possibly, if you want to throw in astatine, although it's in such a small, minute quantity on Earth and it's not real stable, so we don't generally work with that. But those would be considered what are called the semimetals or metalloids. There should be an A in there. M-E, here, I'll just write it separate. M-E-T-A-L-L-O-I-D-S. All right. So let's talk about what some of these properties are. Let's talk about what some of these properties are, and what makes metals metals, what makes nonmetals nonmetals. Okay. Sticking with our color scheme over there, we'll go back to red for our metals. Metals are going to be shiny. Some people say they have a luster to them. Now, when you look at some metals, they're not going to look shiny because they're corroded on the outside. However, if you do cut them, you will see the shiny area to them. So they're going to be shiny. They're usually a solid at room temperatures. There's one exception to that, mercury. Mercury is a liquid at room temperatures and pressures. As far as its properties, metals, they tend to lose electrons. They are malleable, meaning that you can pound them into thin sheets. They are ductile, meaning you can draw them into thin wires. I'll put that in parentheses, sheets. You can form them. Ductile, meaning you can make them into wires. And they're going to be conductive. Conductors of heat and, it's an and sign, electricity. Heat and electricity. Now, on the other hand, nonmetals are just not metallic. So therefore, if metals are going to be shiny, nonmetals, when they're solids, are going to be dull. Where metals are going to usually be a solid at room temperature, nonmetals can be solids, liquid, or gas. They have variable phases. Where metals are going to lose electrons, nonmetals tend to gain electrons. Where metals are malleable and ductile, meaning that you can bend them, form them, draw them into wires, etc., nonmetals are going to be brittle when solid. And while metals are good conductors of heat and electricity, nonmetals are insulators. So it's not that nonmetals have their own set of properties, it's just that their properties are not metallic. Now, once again, in the middle somewhere, you have, because this is a variable or a continuum type of a thing, you have some elements that exhibit properties of both metals and nonmetals. I'll put this in green. So metalloids, it's hard to say what their appearance is because it really depends on what they are, but let's take a look at, say, silicon. Silicon is going to be shiny like a metal, but brittle. All right, like a nonmetal. It will conduct electricity well, but not heat as well. When we say heat as well, it will heat up, but not nearly to the extent of metals. When you take a look at its chemical properties, it definitely behaves as a nonmetal. It doesn't react with a whole lot in terms of the things that we use here in class anyway. All right, so that's what we mean by a semi-metal or a metalloid. They're going to share properties of both. Now, there may also be exceptions to other rules. For example, carbon is definitely classified as a nonmetal. However, one form of carbon, graphite, will conduct electricity. All right, but that doesn't mean that we're going to all of a sudden classify carbon as a metalloid. However, if you look where it is on the periodic table, all right, it is very, very close. In fact, it is touching the staircase that runs down the periodic table, but we do not classify carbon as a metalloid. Some people I have seen on one list, they've included aluminum as a metalloid. 95% of the time, it is not. It is classified definitely as a metal. All right, but again, the whole idea here is that this is a continuum. We don't have perfect metals, perfect nonmetals, and then a certain category called semi-metals. There are some metals that are more nonmetallic than others. There are certain nonmetals that are more metallic than others. And then we arbitrarily will say and classify certain substances as semi-metals or metals because they are such a hybrid that it warrants them being classified something else. But they don't know exactly what they are. These classifications are simply our ideas. Okay? All right, that concludes 6.1. In 6.2, we're going to take a closer look at the families on the periodic table.